Hello, everybody. Good evening or morning or afternoon, whenever you're deciding to give this a watch. I wanted to create two short videos showcasing some things that we didn't get to in lecture on whatever day it was, Wednesday, right? So what we're going to talk about here is a continuation of the Earth's energy balance and why we talk about it or why we study it, what the point is, right? And then there will be a separate video talking about albedo and why that is important. So here we're going to go ahead and give this a go. Boop. Okay, so why study the Earth's energy? What's the point? Well, the Earth's energy budget helps determine the temperatures of the Earth. We must understand this in order to talk about climate change. Several of us pointed things like this out in the Jamboard discussions that we had in class on Wednesday. There's also this uneven distribution that drives motion in the ocean and atmosphere, right? So imagine Earth. Give me back here. So imagine planet, right? Planet Earth, and we have the sun. Actually, I'll use my light source here. Sun is beaming on it. But notice how, this is actually a pretty decent demonstration. Notice how it's pretty sharp on the back of my hand. But then the same light, the same amount of light is now spread out over the tip of my fingers. So see how it's kind of not as bright there. So what happens is then we have this surplus of energy in the equator and a deficit at the poles. And this uneven distribution drives things like mid-latitude cyclones, tropical cyclones, any sort of other storm motion that you could think of. It drives ocean currents. That's why we have, all the ocean currents that we do, because it's helping redistribute that energy and that heat or lack of heat, right, around the planet. So then some various goals for this lesson include understanding that real objects in the world end up emitting a range of different colors or wavelengths rather than one single color or wavelength. And then understand how temperature then affects the amount of energy that's emitted and the wavelength of the peak emission. So we noted in class already that in simplistic terms, right, we started thinking of hot objects as emitting a single color or wavelength of light, right? We had those examples of the flames, right? The red flame and the blue flame. And we indicated that one, of course, was hotter than the other. And some discussion questions to ponder, right? Does the sun emit just one color of light or more than one color of light? And how do we know this? We talked about this before, but Nub does not remember. So maybe pause for a second, think about it. All right, let's revisit. So remember that the sun does actually indeed emit all wavelengths of the visible spectrum. So this is a graph showing the emission of the sun on an idealized form, right? On our x-axis here is our wavelength in nanometers, and our y-axis is intensity in a somewhat arbitrary unit. And this is really the classic Blackbody curve. Which direction gives increasingly energetic photons? The key point here really is that the hot radiating object does not emit a single wavelength, as our original discussion suggested, right? Instead, it emits a spectrum of wavelengths. And let's do some checks to see if this is consistent with what we already know, right? Do hotter objects emit more energy? Are blue emitters hotter than red emitters? Are the temperatures at which you get visible light sun-like temperatures? Yes! But something else is happening here, right? Objects are emitting more than one wavelength. In fact, hot objects emit many different wavelengths of light, right? But the peak energy shifts to a higher frequency as the object warms. Notice here how we have our lovely sun, which is at that of yellow, or this is why one of the reasons why we see the sun as being yellow, right? This is the peak wavelength of the sun, but we're able to see all of these wavelengths. This is the whole visible spectrum, but the peak here is where the color of the sun, and that's what we see. Again, so yes, we say the sun is yellow because there's more yellow than any other color. And here's another visualization of that, right? Again, this is an idealized situation. This was a graph that we've looked at already, but just to revisit here and just to showcase that the sun does emit at various wavelengths, but it's the peak at yellow, and that's why we see yellow as our sun, as the color of the sun. Okay, so once again, looking at this black body curve here. Same similar idea. So objects emit at a range of wavelengths. And it depends on the temperature, right? And that's a pretty interesting observation as well. So the amount of total emissions increases with temperature, right? So cooler objects emit a broader range of wavelengths. And temperature also determines our emission flux in watts per meters squared. And we can see this here on our graph, looking at temperature on the x-axis and power on the y-axis. Right, so our boiling water takes a lot of energy, right? And that is our flux, and it's really hot to boil water. So again, looking at this space here, and as we go up the curve, where that peak emission goes and where that wavelength is at. Yeah. Wavelength or color of peak emissions, again, shifts with temperature. The big old point there. So, a little trick question. But for much cooler temperatures, so these are getting closer to Earth-like temperatures, but not quite there yet. We are quite chilly. So what color will a 1,500 K object look to the human eye? We wouldn't be able to see it, right? It would be in a different wavelength, more close to the infrared, right? So again, some important points here. Hot objects emit energy as radiation. We already determined that, right, when we compared the apple and the burner emission. All objects emit at a range of different wavelengths. Yes, ranges. The hotter the object is, the more energy it emits. And temperature of an object controls the color or the wavelength of that light that it emits most strongly. Go back to that graph of the black body curve and seeing that yellow is the peak. So thus that is the color of the sun that we see. Flux is another important point here, yeah? So for solar energy, we care about the power of sunlight over a surface of the solar panel. That is flux, right? If I'm putting solar panels on my roof, I don't care about the rate at which the sunlight falls on the planet as a whole. I don't care. What I do care about is how much solar energy is then intercepted by the solar panel. So I care about flux of solar energy per unit area, right, in watts per meter squared. Visible and infrared radiation are tracked both as fluxes. And it's interesting, and this will bring us to our second point in the second video. Here is Earth. Hi, Earth. You're cute. So we always have light coming on half the disk, yeah? But do we always have energy coming out of our planet? Yes. So at night, we're always emitting energy. Yeah, everything that's above absolute zero is emitting some sort of energy. And the planet itself, is emitting at a longer wavelength, longer than that we can see, obviously, when it's long wave infrared radiation. So our flux in, of course, is the amount of visible light into Earth, and then our flux out is the infrared radiation out of all of the Earth, right? We think about the entire planet in that sense, not just half, Let me know if you have any questions. Maybe that was a little bit confusing, and fair enough if it was, but we can work through it, I promise. Thanks for listening.